Imagine you're trying to follow, like a really complex cooking recipe, but you are forced to chop every vegetable, stir every pot, and plate every dish strictly to the beat of a metronome.
Oh, that sounds awful.
Right. It doesn't matter if you're slicing a soft tomato or, hacking through a tough squash. Every single action must take exactly the same amount of time. It would be an absolute disaster.
You'd ruin the meal.
Exactly. Yet, that is exactly how the industry is currently training our most advanced robotic AI models. We are forcing them to operate on this rigid artificial clock. Welcome to AI Paper Slap, where we summarize the latest AI and tech papers for technical folks, ML engineers, and researchers who want the unvarnished mechanics of the absolute bleeding edge. I'm your host, and today we are breaking down a massive release from the X-Square robot team, published in June 2026, called Wall WM Carving World Action Modeling at the Event Joints.
Yeah, and to jump right into it, the authors of this paper looked at the current landscape of world action models, WAMs, and they identified this fundamental flaw they call the granularity mismatch. Because currently, the standard practice is to take a multimodal or video foundation model, bolt an action head onto it, and just force it to predict fixed-length action chunks, say like 50 time steps at a time. Wall WM throws out that clock entirely. They rebuild the architecture to use semantically coherent action events as the atomic unit of learning. They're literally carving the modeling at the event joints.
And the technical stack they use to pull this off is just, it's essentially a master class in modern ML engineering.
Oh, absolutely.
Like if you are building multimodal models right now, you really need to pay attention to this. They deploy a dual tower vision language action architecture to totally avoid the pitfalls of latent action codebooks.
Yeah.
They solve the multi-camera hallucination problem using novel cross-view spatial temporal attention mechanisms, specifically sight cone and tube patch masking. And for inference, they introduced this thing called staircase decoding, which uses a frozen VLM to inject localized reasoning into the action stream.
Which is huge. And then on the systems side, they provide this brutal, highly optimized recipe for scale. They've got a custom distributed muon optimizer, FP8 Quantization, to push inference latency down to real-time physical limits. It's wild.
It really is. Okay, let's unpack this. Because all of that infrastructure culminates in state-of-the-art generalization across reasoning, dexterity, and physically grounded video prediction. But to understand why all that complex infrastructure is even necessary, we have to look at why that metronome approach I mentioned earlier is so destructive to a model's underlying intelligence.
Right. The researchers defined this whole problem through a concept called Modality-Manifold Alignment.
Because the geometries of language, vision, and physical action are fundamentally incompatible if you try to map them uniformly, right? Like, language is incredibly coarse. If you tell a robot to, pick up the mug, that text just describes a high-level semantic goal.
Yeah, it's just a few words.
But then vision is denser. It evolves through continuous scene dynamics as the camera tracks the arm moving toward the mug.
Exactly. And then physical action operates on this hypersensitive control-level timescale. Feeling the slip of the ceramic, the torque on the wrist, that requires the absolute finest possible temporal precision.
So forcing all three of those misaligned modalities into the exact same fixed-length prediction window creates this devastating side effect for your training loss. The authors actually call it short horizon correlation fitting.
Yeah, that's a great term for it. Because when you tell a network to just, predict the next 50 frames, regardless of what is actually happening in the physical world, the model basically abandons any attempt to learn the deep compositional physics of the scene.
It just gives up.
It totally gives up.
Yeah.
It realizes it can minimize its loss function much faster by finding cheap, localized action shortcuts.
So it stops trying to understand the overarching concept of grasping and just tries to mathematically survive the next 50 frames of tensor calculations.
Precisely. Mm-hmm. And that implies that the rigid chunking actually overwrites the valuable visual semantic prior you originally got from your video foundation model.
Yeah.
You end up with a really brittle set of heuristics instead of a generalizable world model.
Wow. So the network essentially lobotomizes its own reasoning capabilities just to satisfy the arbitrary temporal constraint of the chunk.
Yeah, exactly. If we connect this to the bigger picture, the paper actually addresses this by looking back to a quote from Plato's Phaedrus, which is, "Carve nature at its joints."
That's where the title comes from.
Right. The X-Square robot team argues that a world action model must slice embodied dynamics based on semantic events.
Yeah.
Reaching, closing a gripper, lifting. The duration of the chunk has to be dictated dynamically by the event itself, not by an external clock.
Which makes perfect intuitive sense. but it introduces a massive architectural nightmare. If these modalities have completely different neighborhood structures where, like, two identical text instructions might require wildly different visual and physical trajectories, how do you actually align them? Because the trend in latent action papers right now is to just crush the rich visual dynamics down into an undifferentiated, discrete action codebook, right?
Yes. They basically force a latent space bottleneck.
Mm.
But the authors of WALL-WM actively reject that latent bottleneck trend because they recognize it as a massive scaling trap.
How so?
Well, if you compress your dynamics into a discrete codebook, you have to guess the dimensionality of your action space in advance.
Oh, I see.
Yeah. So if the robot encounters a complex physical situation that outgrows that predefined dimensionality like a sudden slip recovery, the model physically cannot represent the required nuance. The bits just aren't there.
So to preserve the geometry of the alignment, WALL-WM uses video as an embodiment-like bridge.
Exactly. Because video sits perfectly in the middle of that density spectrum.
Right? It has enough semantic structure to align with coarse language because you can easily caption a video of an event, but it is temporally dense enough to expose the microtiming and state changes required for physical action.
You nailed it. And to leverage that bridge, they built a pixel space dual tower setup. So you have a video tower and an action tower running parallel to each other.
But how do they actually talk to each other without that bottleneck?
The magic happens in how those two towers communicate. Instead of a hard bottleneck, they use layer-wise coupling and ADLN. That's adaptive layer normalization modulation.
Okay, so the ADLN acts as like a dynamic valve between the vision side and the action side.
Yes. It creates an emergent, permissive, latent action space. If the physical dynamics suddenly become highly complex, the network uses that ADLN modulation to simply open the valve wider.
Oh, wow.
Right. It allocates more parameter capacity to the action side for that specific moment without ever collapsing the rich pixel space representations of the video tower.
That is so smart. It gives the architecture elasticity. The model decides how much capacity it needs frame by frame, rather than being hard-coded by an ML engineer before training even starts.
Exactly. It's fluid.
Here's where it gets really interesting, though. Dealing with rich pixel space representations introduces another major hurdle for anyone scaling multi-camera models.
Oh, the 3D geometry problem.
Yeah. Because if you are building a robotic system, you are dealing with multiple views. You've got egocentric cameras, third-person tracking, wrist-mounted sensors. If you just throw multiple camera views into a standard self-attention block, the model inevitably starts hallucinating impossible 3D geometries.
It absolutely does.
It will try to attend to a patch of a coffee cup from a left-side camera and blend it with a background patch from a right-side camera, completely destroying the spatial coherence.
Because the standard self-attention mechanism has no inherent understanding of physical space. It only looks for statistical correlations.
Right.
But WALL-WM implements a series of solutions inside their WAN VAE layout to force the model to respect 3D geometry. The first one is a zero initialized output projector on the cross-view attention branches.
Wait, so by turning the cross-view exchange off at initialization with zeroed-out weights, the model is forced to process each camera view entirely independently at the start of training.
Yes. It protects the pre-trained appearance and language alignment behaviors. The network is given time to stabilize before it slowly learns how to safely route information between the different views.
That's a clever trick. But the really elegant math is in how it determines what is actually safe to route, right? Which they solve through sight cone masking.
Yeah, sight cone masking transforms self-attention into a physics-bound operation. The model uses camera rotary position embeddings to tag which specific camera a token originated from. Then it calculates a deterministic binary mask based on the actual physical intersection of the camera sight cones in 3D space.
So think of the cameras as flashlights shining into a room.
Exactly.
If the beam of camera A intersects with the beam of camera B over a specific region of space, the model allows attention to flow between those patches.
Yep.
But if those flashlight beams do not physically intersect, the model applies a negative infinity bias to the attention matrix for those patch pairs. It mathematically forbids the model from routing information across geometrically incompatible patches.
Right. Because you cannot attend to a spatial region from a secondary camera if that camera could not physically see it in the real world.
Yeah.
This completely prevents the hallucinated blending of uncorrelated pixels. And the paper actually takes that a step further with two-patch masking to actively induce 3D understanding.
Oh yeah, during training, they randomly select a spatial window, they call it a tube, and just black it out across all frames of specific camera view. So if the left camera is looking at an apple, they just replace the apple with pure noise for that entire sequence.
Yes. And because of the side cone masking, the network is aware that the right camera also possesses a valid view of that spatial region.
So the only way the model can minimize its reconstruction loss and recover that masked tube is by successfully routing its attention through the other camera views.
Precisely. It forces the network to internally build a functional 3D model of the scene to recover missing 2D patches.
Yeah.
Entirely without relying on explicit point clouds or depth maps.
That is incredible. But okay, that brings us to inference, and I have to push back on a choice the authors made here.
Let's hear it.
We just spent all this time establishing that fixed-length chunks destroy reasoning. That is the core philosophy of their event mode rollout, where the model consumes an event description and outputs a dynamically sized action sequence based on how long the event takes physically.
Right.
But then the paper outlines a unified mode for inference that deliberately uses fixed-length chunks. Isn't that just a complete contradiction of their own thesis?
I know, it seems completely contradictory until you look at the mechanism driving the chunk. The problem with traditional WAMs isn't just the fixed length itself, it's what the fixed length is conditioned on.
What do you mean?
In a standard model, a 50 time step chunk is conditioned directly on a raw global instruction like make a cup of tea. That text is vastly too coarse to guide a highly sensitive control output. Wall-WM's unified mode fixes this through staircase decoding, which places an intermediary reasoning layer between the global text and the local chunk.
Ah, right. They use a frozen lightweight vision language model, specifically Qwen 3.5 down 0.8b, to act as that intermediary.
Yes. So the first latent position of the sequence traverses the lower transformer layers of the model, producing a shared relay representation. This gives you a deeply grounded visual state of the world at that exact microsecond.
And then that relay representation is projected via a prefix projector directly into the frozen Qwen model.
Exactly. Qwen takes that highly specific visual state, combines it with the global instruction, and auto-regressively generates a latent event representation. It creates a localized chain of thought trace.
So it is essentially whispering to the action model, the global goal is making tea, but right now, at this exact millisecond given your wrist position, your sub-goal is to adjust the angle of your grasp on the kettle handle.
That's a perfect way to describe it. That event-structured latent representation is what feeds into the upper transformer blocks to guide the generation of the fixed-length action chunk.
So the output chunk remains a fixed length, which you absolutely need for hardware batching and deployment latency, obviously.
Yep.
But the gradient continuous path ensures the chunk is driven by deep semantic event-structured reasoning rather than just blind statistical correlation.
Exactly. You get the best of both worlds. The reasoning of event-level planning with the hardware efficiency of fixed chunks.
But achieving that level of semantic event-structured reasoning creates a massive computational bottleneck. I mean, you can design the most beautiful dual-tower architecture in the world, but if you don't rewrite the systems infrastructure to handle it, the math will literally melt your GPUs before the model learns anything.
Oh, absolutely.
This is where the paper becomes a total goldmine for ML engineers. They opted to use the muon optimizer because of its fantastic convergence properties, but vanilla muon requires a Newton-Schultz iteration step to achieve matrix orthogonalization.
And that is not cheap.
No, that operation is so heavy that the optimizer step alone can take twice as long as the forward and backward passes combined.
Right. So the authors had to fundamentally redesign the optimizer for distributed execution, creating what they call d-muon distributed muon.
How does that work?
Well, in a standard PyTorch data parallel execution, every single GPU in the cluster attempts to handle these massive matrix orthogonalization operations synchronously. D-muon implements the longest processing time assignment to decouple the optimizer step entirely.
Okay, so they map specific matrix parameters to unique ranks across the cluster, replacing native all-reduce operations with an asynchronous reduce and broadcast system that runs on a dedicated CUDA stream.
Yes. This allows them to overlap the brutal Newton-Schultz computation with the forward pass of the next training step.
So they're turning a blocking bottleneck into a hidden background cost.
Exactly.
Yeah.
But they didn't stop at the cluster level. They went down to the actual kernel math.
Right, because the Gramian formulation inside muon naturally produces a symmetric matrix structure.
Yes. And standard general-purpose matrix multiplications, GM operations, are totally blind to symmetry. They calculate the entire matrix, meaning you are spending nearly 50% of your compute budget calculating values you already have.
Just a massive waste.
Huge waste. So the researchers wrote custom, shape-aware, auto-tuned kernels using Q to DSL that only compute the necessary factors of that symmetric structure.
They instantly reclaimed half of their compute budget just by respecting the geometric properties of the math.
That's brilliant.
And they applied that exact same scrutiny to their sequence parallelism. Because they are processing video, they use Ulysses sequence parallelism to handle massive context lengths.
Right.
But Ulysses works by slicing the video sequence across different GPUs. If you combine that with the cross-view attention we discussed earlier, you create a massive traffic jam of data. A naive implementation would require 4 back-to-back all-to-all communications across the network per layer. The communication overhead would completely throttle the cluster.
So to prevent the hardware from becoming network-bound, they implement fine-grained overlapping. They physically hide the all-to-all communication payload underneath the matrix multiplications of the attention computation.
So as the GPU is busy crunching the attention scores for its local tokens, the tokens from the other GPUs are arriving over the network in the background, landing just in time for the next computational step.
Exactly. It requires an unbelievable level of orchestration to pull off.
Yeah.
And that engineering rigor is also how they achieve their required inference speeds.
Right, because a diffusion-style world model typically requires tens of denoising steps per frame. You cannot run a 50-step diffusion process inside a 100 Hz physical control loop on a robot. The latency is just way too high.
Far too high. They use progressive distillation to drop the denoising step count, but the real unlock is FP8 quantization.
Okay, let's talk about that, because many deployment architectures rely on INT8 quantization to reduce memory bandwidth. But the authors explicitly note that INT8 fails catastrophically for large transformer models.
It really does. The activations inside transformers produce heavy-tailed distributions with massive channel-wise outliers. INT8 allocates its fits uniformly across the entire range.
So it either clips the outliers, destroying your model's accuracy, or it stretches its resolution so far that it crushes the precision of the normal values.
Yeah. Think of INT8 like a standard 12-inch ruler. It's great for measuring everyday objects, but totally useless if you need to measure bacteria or the distance between galaxies simultaneously.
Good analogy. FP8, however, uses an exponent mantissa split. It acts like a microscope and a telescope built into one. It shifts its scale dynamically.
Yes. It can represent incredibly large numbers and incredibly small numbers with high fidelity. Paired with per-block scaling, where the scaling factor is calculated over a small localized block of waves rather than the whole tensor, they preserve the crucial outlier data while cutting the memory footprint in half.
It's just so robust. But, all of that optimization overhead and parameter width implies an absolutely massive influx of training data. You cannot scale a dual tower model without feeding it appropriately. Their data ecosystem mixes general internet video from OpenVid, egocentric video from Ego4D, and heterogeneous teleoperation.
Not true.
But I have to question the utility of general web video here. I mean, a YouTube video is inherently clean. It shows a human successfully performing a task. It does not show a robot failing, slipping, or recovering from a botched grasp. If the model only learns from successes, how does it know what physical causality looks like when something goes wrong?
That's a great point, and the researchers anticipated that exact gap. Web scraping is totally insufficient for embodied control on its own. So right in the center of their data set is a heavily curated category of human intervention and failure recovery data, and they collected it using a very specific recovery mixture formula.
So they don't just passively record data.
No, they actively map the failure space. They take a successful teleoperated trajectory, pause it at the exact moment of a contact event, like a gripper touching a block, and deliberately perturb the robot's physical state.
Oh, wow. So they knock it off balance, shift the object, change the angle.
Exactly. Then a human operator provides a fresh recovery rollout from that broken state. By forcing the model to learn contact-rich corrections around event boundaries, they teach the WAM the actual physics of recovery.
That makes a lot of sense. Because failure states are incredibly sparse in nominal data, and simple clustering algorithms will completely miss them. This perturbation ensures the model doesn't just memorize a smooth, happy path trajectory, but actually learns how to navigate the messy realities of friction and gravity.
Exactly. And what's fascinating here is how the paper concludes with this profound philosophical argument about how the field evaluates all of this. Because the standard assumption in robotics is that real-time latency is a strict, non-negotiable constraint.
Right. If your model can't run at 100 hertz out of the gate, it is considered useless.
But Wall WM argues that enforcing latency constraints too early in the research phase artificially caps the model's generalization ceiling. The authors argue that we are handicapping our models before they even learn how the world works.
Their thesis is that you must scale for generalization first.
Yes, you leverage massive parameter counts, dual tower architectures, and heavy compute to teach the model the deep semantics and compositionality of reality.
And then, once the model actually possesses a robust physical intelligence, you treat latency as a solvable engineering problem.
Exactly. You use progressive distillation, FP8 quantization, and d-muon overlapping to speed it up. Recovering a lost generalization ceiling from a model that was kept small just to meet a latency target is almost impossible.
But making a deeply intelligent, over-parameterized model run faster, we have the math and the infrastructure to do that.
We do. It demands a massive shift in priorities for anyone building foundational architectures. The intelligence must come before the speed.
So what does this all mean? It leads to a much larger question for you, the listener, as you look at your own modeling pipelines.
Yeah.
We started by talking about the granularity mismatch in robotics, where forcing a model to operate on a rigid clock destroys its reasoning. But if true physical intelligence comes from carving reality at its semantic joints, rather than processing the world in uniform time steps, what does this mean for the future of broader AGI architectures?
It's a huge question.
Are our current autoregressive large language models fundamentally limited because they are trapped predicting uniform text tokens instead of conceptual temporal events? Are we forcing the mind of an AGI to chop vegetables to the beat of a metronome?
It's definitely a paradigm shift. It changes how we think about the representation of time itself in machine learning.
It really does. Well, that is all for this deep dive into the source material for AI Paperslop. Check out the X-Square Robot Team's GitHub repo for the actual code behind Wall WM, and keep questioning the priors in your own models. See you next time.